Here are some notes on conditional probability. The first one is conditional probability, like unconditional probability, obeys the probability axioms and their spin-offs. So for example, we know all probabilities lie between 0 and 1 inclusive. Well, that means that all conditional probabilities will also lie between 0 and 1 inclusive. Second of all, the probability of event A occurring, given it occurred, is 1. So basically, if we know that A has occurred, then we know with certainty that it will occur. And so that has probability 1. Third, if you look at our definition of conditional probability, that is, probability of A given B is the probability of their intersection divided by the probability of the given event B. It turns out the events A and B can become arbitrarily complex. So for example, if we replace A here with A intersect B prime and we replace B with C, then we just know it's the probability of the intersection of the two events divided by the probability of the given event. Likewise, if we want the probability of A given B prime union C, it's the probability of the intersection of those two divided by the probability of the given event. So the takeaway from that third note here on conditional probability is A and B can become arbitrarily complex. The fourth note is that if A2, A3, etc. are a bunch of disjoint events, and in fact, let me go ahead and draw a Venn diagram for this case. If this is your sample space S, and you've got A2, A3, etc. being disjoint events, let's draw them this way. Here is A2, and here is A3, and we might have A4 up here, and maybe we'll put A5 here. That's enough. Then the probability of the union of those events given A1. Now A1 is an event. I'll just draw it in here. Better label it from the outside. A1 is this event right there, which intersects some of them but not others. That will be the P of A2 given A1 plus probability A3 given A1 plus probability A4 given A1, etc., provided P of A1 is non-zero, because that is the given event and you don't want to have a zero in the denominator. That looks quite a little bit like one of the axioms. That's like a conditional version of axiom 2. And finally, the last note, there is something which unfortunately is called the multiplication rule. That makes it a little confusing because we used a multiplication rule in counting techniques. But in any case, if you take this expression and you simply solve it for the probability of A intersect B, you can see that's quite easy in this case. You just multiply through by P of B. Well, when you do that, you get P of A given B times the probability of B. And likewise, if we just swap the roles of A and B here in this particular expression, this would look exactly the same, but we'd have a P of A in the denominator. You get this, and this is known as the multiplication rule. And it's amazing how much mileage you can get from that particular result.